Hi, this is Professor McKinsey, and I'm putting together a video to look at problems 10 and 11 from the worksheet involving computing probability. These were two problems involving um, five-card poker hands from a deck of playing cards. I want to look at problem 10 first. It's the easier of the two, but I want to look at some aspects of this question that I think might shed a little bit of light on question 11 as well. So the question was, how many different five-card poker hands are there? Poker is played with a standard 52-card deck of playing cards. And the quick and sort of direct answer to this is to simply observe that a deck of playing cards has 52 distinct objects in it, and we're asking how many different ways there are of choosing five of those objects out of the deck. And so 52 items, or counting the number of ways of choosing five of them, would be 52 choose five, which we can expand as 52 factorial divided by 5 factorial times 47 factorial, which if we expand out 52 factorial as 52 times 51 times 50, 49 times 48 times all the numbers up to and including 47, we see that we have 47 factorial as a common factor between the numerator and denominator. And then we actually can find some additional common factors as we finish reducing that. Where if we cancel the remaining common factors between numerator and denominator, uh, we find that all of the factors in the denominator are able to be canceled out, which is what you would expect, since after all, this fraction is meant to be measuring a natural number, the number of different ways of doing something. And when we compute our product, we end up with our final answer of 2,598,960. So that's the answer to number 10. Um, I want to comment just very briefly on a different way you might have thought about this problem. Actually, there are a couple ways I'm going to look at. One of them, which is incorrect, and I want to talk about why it's incorrect, and another which actually is correct, and a rather powerful way of thinking about drawing cards from a deck and similar sorts of problems. So, with a little bit of hesitancy, let me talk about a bad way of doing this, a way that doesn't work, and then we'll talk about why it doesn't work. You might think about doing the MN principle, the multiplication principle, because if we're going to draw five cards from the deck, first we're going to draw our first card, and there are 52 ways of doing that. And once we've drawn our first card, then there are 51 cards remaining. And so there'd be 51 remaining ways of drawing a second card. And then if we draw a third card, there are 50 cards left once we've drawn the first two, and so on. We might decide that the total number of ways of drawing five cards out of a deck is 52 times 51 times 50 times 49 times 48. Now, this answer differs from our previous answer because we're not dividing this answer by 5 factorial. And in fact, that gives a hint as to why this answer is wrong. We've overcounted every hand. Every single possible hand gets counted 5 factorial, 120 different times under this counting scheme. And here's why. Suppose that the 5 cards that you pick out of the deck are the ace of hearts, the 3 of clubs, the 4 of diamonds, the 2 of spades, and the 5 of clubs, in that order. We would count this hand. Well, one time we would count it would be drawing the ace of hearts first. That'd be one of our 52 options for the first card. Then following that by drawing the 3 of clubs second. Then drawing the 4 of diamonds third, the 2 of spades fourth, and the 5 of clubs fifth. However, any reordering of these 5 cards would be counted separately in this product of 52 times 51 times 50 times 49 times 48. Maybe we would have done the 4 of diamonds first, followed by the 2 of spades, followed by the 3 of clubs, followed by the ace of hearts, followed by the 5 of clubs. That's another sequence in which we could have drawn those 5 cards. It's the same poker hand. It's the same 5 cards in your hand, but it would have been counted separately in our product 52 times 51 times 50 times 49 times 48. And in fact, there are a total of 5 factorial different rearrangements of these 5 cards. It's why the product we wrote out is too large by a factor of 5 factorial. And in fact, this idea that we're off, that we've overcounted every single possible hand 120 times, 5 factorial times, is the principle behind the proof in the book that that our choice function 52 choose 5 is the appropriate function for counting the number of 5-card poker hands. So now that we've seen how not to solve question 10, along with the actual solution to question 10, I'm going to move on to question 11. How many poker hands consist of a pair, 2 cards that have the same rank, with the other 3 cards having non-matching ranks, such as, and then this example where we have a pair of jacks followed by 3 other cards, none of which are jacks, and significantly, none of which match one another. So the first part of the question is, how many poker hands are there that fit that description? And then the second part, what is the probability of drawing a pair in poker? The second part is just going to be the ratio of our answer in number 11 to the 2.5 million that we found in problem 10. So we want to count the number of poker hands consisting of a pair. Now, in order to get a pair, there are 2 things that you need to do. And we can use the MN rule. So the first thing we're going to do is count the number of possible pairs, or the number of ways to get a pair when you draw 2 cards. And that won't be too bad. Counting that is fairly easy. So the first thing we're going to do is get a pair, whether it's a pair of jacks or a pair of aces or a pair of threes, whatever it is. And then we're going to need to multiply that by the number of ways to fill in the remaining 3 cards. And what's complicated here, and this is really where most of the trouble comes, is that we don't want just any old 3 cards from what's left in the deck. We want to make sure that we don't match the rank of the card that we had for our pair. So I want to make sure that none of the 3 remaining cards are jacks in our example. And also, I want to make sure that none of the cards that I end up drawing match one another. I don't want to have a 2, an 8, and an 8, for example, because then I wouldn't just have the pair of jacks, I'd also have a pair of 8s. So the first thing I'm going to do is count the number of ways to get a pair in 2 cards drawn from the deck. And I can think of a couple of very different ways of counting that. One way to count this using the MN rule would be to count first the number of ways we could draw our first card. So that would be 52, or if you'd rather, you could say 52 choose 1, but that just simplifies to being 52. There are 52 choices for the first card, and then, well, if we just wanted to count drawing any old card for the second card, there'd be 51 ways of doing that. But if I want to make sure the second card matches the first card, well, if the first card was an 8, for example, there are only 3 8s left in the deck. And so 52 multiplied by 3 would count the number of ways of drawing a card of some sort out of the deck, and then drawing another card that matches it. Now, from the idea that we saw earlier, where with our failed attempt at counting the number of ways of drawing 5 cards out of the deck, one problem with this count is that any pair of cards will be counted twice. The 8 of hearts being one of the 52, and then the 8 of diamonds being one of the 3, would be counted separately from the 8 of diamonds, being the first card we draw, followed by the 8 of hearts. So since the order in which we draw the two cards doesn't matter, and every possible pair would have been counted 2 factorial many times, we would need to divide that by 2 factorial so that the order in which we draw the two cards doesn't matter. If we simplify this, we end up with 26 times 3, which is 78. It looks like there are a total of 78 possible matching pairs of cards in a poker in a deck of playing cards. A different way that we could have counted the same number of ways of getting pairs of two cards, we could use the multiplication principle. Now, when you have a pair of two cards, you need to pick the rank that those two cards have, and you need to pick their suits. Now, the rank that the two cards will have, since they have to agree, there are a total of 13 possible ranks, or 13 choose one if you prefer. We're picking one out of 13 possible ranks that our pair could have. Are we having a pair of jacks, a pair of eights, a pair of threes, whatever it is? There are 13 ways to do that. Once we know it's going to be, let's say, a pair of jacks, we then have to pick which suit the two cards are going to come from. And there are a total of 4 suits, and we need to pick 2 of the 4. And so a different way of calculating this same quantity, the number of ways of getting a pair when you draw 2 cards out of the deck, would be to multiply the number of ways of picking one rank times the number of ways of picking 2 suits, so that in effect you know what rank you have and you know what the 2 suits are going to be, and so you've completely described the 2 playing cards you're going to draw. And so when we have 13 multiplied by 4 choose 2, we can expand 4 choose 2 as 4 factorial over 2 factorial times 2 factorial. 4 factorial and one of the copies of 2 factorial will reduce. 12 over 2 is really just 6. And so we end up with 6 times 13, which happily 6 times 13 is 78. So it agrees with the result we had before. All right, so we've seen that there are 78 ways in which we can pick our pair that we're going to have in our hand. And now what we need to do to finish the calculation is compute the number of ways there are of picking 3 additional cards to put into our hand. And so I'm going to look at a few different ways of computing this, some better than others, and talk a little bit about what the rationale is behind these. So one possible answer would be 48 choose 3, because we have 2 cards from out of the deck in our hand. They're 2 jacks. So that means there are 50 cards left in the deck, but 2 of those cards match the 2 that we already have. And so there are really only 48 cards left that are not jacks. And of those 48 remaining cards, we want to pick 3. This is not correct, it turns out. And the reason it's not correct is 48 choose 3 would include the possibility that the 3 cards I draw might agree with one another. So I could have 2 jacks, a 5, a 7, and a 7. And 48 choose 3, counting the number of ways of building my 3 additional cards, avoiding the jacks, I didn't do anything to make sure that I didn't draw a pair out of that 48 choose 3. So this is not a horrible answer. There's a lot to like about it. The intuition is good, but it doesn't actually do what we want, because if I'm just trying to count the number of ways of getting only a pair in a poker hand, I don't want to count those situations where I get a hand that's stronger than having one pair in it. So similarly, oftentimes I'll see the response of 50 choose 3 for this piece. You've drawn 2 cards from the deck, leaving 50 cards behind. We're counting how many ways are there, finding 3 more cards to put into our hand. This runs into a similar problem as the previous answer. Not only are we not making sure that the 3 cards we draw don't agree with one another, but this also doesn't ensure that they don't agree with the original jacks that we've drawn.